Hi everyone. So in this video, I will be showing you how to do a simple organic chemistry synthesis problem. In this case, we're given a start alkene and an end alkene and four possible sets of reagents. And we want to figure out which set of reagents, A, B, C, or D, will lead us from the start alkene to the product alkene. So I highly recommend that you pause this video first and try to do this on your own and figure out which set to use. Otherwise, I will begin. So I'm actually going to erase these so I can get some space. And we're going to go through them one by one. There are some tricks that we can do to solve this really quickly, but I think it would be better to just do them one by one. Set A, I'm calling it set A, option A, whatever you want to call it, has our first step being HBr and ROOR. This is just a peroxide. And our second step is performed by Na, indicated in Orgo as OET. This just means sodium ethoxide. So let's deal with step 1 first. Step 1 of this set would have us use hydrobromic acid and a peroxide. What you want to know is that this is the set of reagents you need to perform a free radical addition. And I don't know if for your class or your course, you're going to need to know exactly how this reaction occurs, but I guess I'll just draw it here. Otherwise, you can skip a few seconds ahead if you don't want to see this part. So what's going to happen here is you're going to have your peroxide, and it's going to be bonded like this, and you're going to use your fishhook arrows to break this bond between the O and the R group to get RO and RO. Next, you're going to have one of these RO groups, ROR, same thing, along with your hydrobromic acid. And again, you want to use your fishhook arrows to show them being bonded together. So you're going to get HOR and a free bromine atom, not bromide. There's no negative charge on this bromine. It is a bromide radical. This is not bromide radical, bromine radical. You're going to see 7 valence electrons here, and I have this dot to show that there is a free radical. Next, you're going to have your alkene. I'm going to draw a sample one here, and what's going to happen is, again, you want to use your fishhook arrows. Remember that this pi bond acts as a nucleophile. And so it can perform nucleophilic attacks. And in this case, if you have your free radical bromine here, remember that this bromine kind of wants to hit 8 valence electrons, so it wants to be bound to something. We're going to get this fishhook arrow reaction. So this pi bond is going to be split because it's 2 electrons, and you might remember this from the resonance video I did a while back, a resonance problem with fishhook arrows. I don't remember what it's called, something like that. And you're going to end up with a product that looks like this. And you have a free radical on your carbon-carbon bond. That's where the name comes from, free radical addition, because now remember that you have more HBr in solution, and that's going to allow you to perform the same kind of reaction here. It's going to add an H to the other side, and boom, boom, boom. So this is how you perform this reaction. It's going to lead to the anti-Markovnikov addition of a halogen. So I used bromine in this example. You could use chlorine, you can use iodine, whatever you want. So sorry I spent sorry I spent so much time on that. That's just in case you wanted to see how this free radical addition reaction works. Otherwise, you can just remember that it's the anti-Markovnikov addition of a halogen. So that's going to allow us to, that's going to allow us to figure out what happens here pretty easily. So I'm going to redraw the starting molecule here. And we know that HBr-ROOR is the anti-Markovnikov addition of bromine. I just drew that out. So we're going to add the bromine to the less substituted side of this alkene. Where is that? Well, this carbon over here has 1, 2, 3 different carbons bound to it. So it is a tertiary carbon. This carbon over here is only bound to one other carbon, so it's a primary carbon. This means that this carbon is the less substituted carbon, and so we're going to add the bromine to that side. So I'm going to redraw this with our bromine bonded to the less substituted carbon. Now our next step is going to be the reaction of this product with sodium ethoxide, and just for the sake of having to write less, I'm going to write this out as just the ethoxide ion. And this works because this will dissociate completely. So the sodium has a positive charge, ethoxide has a negative charge. And this ethoxide, we have to remember that it can be both a strong base and a strong nucleophile. That means that it can perform either E2 or SN2 reactions. Now, if we have this alkyl halide rather, reacting with ethoxide, what kind of product do we expect? Well, ethoxide can be a strong base or a strong nucleophile, so it can attack either a carbon or a hydrogen. So in order to figure out what it will do in this particular case, we need to look at the alpha carbon. So that would be the carbon bound to the halogen. So this bromine is bound to this carbon. This is our alpha carbon. And we see, as we saw over here actually, that this is a primary carbon. Now, primary carbons have very little steric hindrance. They're only bound to one carbon. So if you want to think of it like this, you have your carbon bound to hydrogens, right? Well, if we think of the orbitals, right? The orbitals of a hydrogen atom, or rather this shared hybridized orbital, is much smaller than the orbital shared by carbon and carbon. And so any kind of, I like to think of it as a fight sequence, so any kind of attack from a nucleophile, like a punch, these carbons over here are going to almost serve as protection from any kind of nucleophilic attack. Whereas if you have mostly hydrogens, you're going to be able to attack it very readily. There's a lot of empty space because these orbitals are much smaller. So if we have a primary carbon, meaning that this carbon is only bound to one other carbon, there's going to be a lot of room on the backside for the ethoxide to attack as a nucleophile. And so to draw that out using curved arrows, I like to use red for my curved arrows. We're going to have a backside attack on this carbon to perform an SN2 reaction. And so what we'll get is this product here. This is going to be our product with reagent set A. So we compare that to our desired product. This is not correct. This is not, these do not match up. In fact, we're actually missing a whole double bond. So this is completely off. So this is not, let me write it next to A. A is not correct at all. Okay, so we can eliminate choice A. Okay, well, what about choice B? So choice, let me zoom in actually a little closer. So choice B had just HBr, hydrobromic acid, as the first step, and our second step involved a molecule called TBUOK, potassium tert-butyl oxide. Well, let's start with step 1, HBr. So let's draw out our starting alkene. Remember that fundamentally, on some basic level, you know, it's not, this is kind of an oversimplification of how alkene reactions work. But fundamentally, everything that you're going to see with the alkenes is going to have this pi bond act as a perform a nucleophilic attack, and it's going to remove, I'm going to call this X and Y. It's going to remove X from this bond, and it's going to separate them. So you're going to have an addition of X to this side. Fundamentally, that's how all of these alkene reactions are going to occur. Now, that's a bit of an oversimplification, because as you start to get to more complicated alkene reactions, you're going to start to see, different variations on that. But it's a good concept to know that this pi bond is going to perform a nucleophilic attack. Okay, so let's see what happens when we have HBr, hydrobromic acid. Well, in this case, our pi bond is going to perform it's going to perform a proton transfer step. It's going to attack this hydrogen, and this bond is going to break. So what we'll end up getting is this product. Actually, normally we don't draw hydrogens on these structures. There are cases in which we will draw hydrogens on these line angle structures, such as in the case of alkenes, where you need to show a hydrogen. But in this case, the hydrogen is going to get attached to this side. I'm just drawing that there for you to see it, because remember that this pi bond is actually representative of 2 electrons. And so if we're bringing all of this charge to one side by adding a hydrogen, we're creating a positive charge on the other side of this bond. So it's going to form a carbocation. Carbocation. It's one word. So I guess I'll try to squeeze it in here. And this carbocation, one thing that we absolutely have to remember, it's not going to happen in this case because this carbocation is already on a tertiary carbon, but be very careful of methyl anhydride shifts, because this carbocation is going to move to any adjacent carbons that are more substituted, or that can better stabilize that positive charge. So that's not going to happen in this case because the carbocation is already on a tertiary carbon. But just remember that to be very careful of where this carbocation will go, where this positive charge will go. And that's why when you perform, this step is actually called the electrophilic addition. It's going to allow you to get the Markovnikov product, or the product that puts one of the groups on the more substituted side. So in this case, electrophilic addition puts the bromine on the more substituted side, because this bromine now has a negative charge. It has a full-on negative charge, and it's going to target a positive charge. Remember, opposites attract. And so this bromine is going to perform a nucleophilic attack on this carbocation, and we're going to end up with this product. There we go. Let me write that a little more nicely. So that is step 1 done. Now step 2 involves a molecule that you might have heard of before called potassium tert-butoxide, TBUOK. So this is a very bulky base. You might have heard about it in your class because it's like the classic bulky base. It actually looks something like this, and then there's a negative charge here, and it's in solution with the potassium ion. It's a bulky base, and it's strong. It's a very strong base. Let me write that down here, which means it's very, very, very good at attacking hydrogens. But look how big this is. This is a big boy over here. It's 1, 2, 3, 4 carbons bound to an oxygen. This thing is pretty big, and that means it's going to have a very hard time abstracting those carbons, especially if those carbons are very highly substituted. Remember, we talked about that concept of substituting carbons, making it harder for nucleophiles to attack. That's called steric hindrance. So this is going to be a very weak nucleophile. So we're going to have an E2. Remember, E2 is going to be the abstraction of a hydrogen by a strong base. So we need to look for hydrogens to attack. So I'm going to label our alpha carbon in blue, and I'm going to label the beta carbons in blue. So beta carbons are any adjacent carbons to the alpha carbon. And now I want to label all the hydrogens surrounding those beta carbons. And this is because these are going to be, I like to think of these as the main points of attack. Where is this TBUOK, where is this strong base going to attack? Well, remember, this is a really big, bulky base. I like to think of it as a gigantic sledgehammer. Like, my mind is drawing a blank as to what fictional giant hammers there are, bigger than Thor's, bigger than Mjolnir, right? And so it's going to have a really hard time striking, these hydrogens that are very sterically hindered. Remember, this hydrogen is shielded by 3 different carbons, 1, 2, 3. So it's not going to attack this hydrogen. It needs to get the hydrogen that is on a primary carbon, because these hydrogens are fully exposed on the flank. And from here, you see 6 possible options, 1, 2, 3, 4, 5, 6. Doesn't really matter which one of these 6 it attacks. We just want to know that it's going to attack an anti-paraplanar hydrogen, one that is 180 degrees opposite to the bromine, but that's really hard to visualize here. It's more easily visualized if we had a ring. We don't have a ring. So for all intents and purposes, I'm just going to have this strong base attacking, this hydrogen. Now, when it attacks this hydrogen, this bond will break. These 2 electrons here are going to be freed to go up here, and that will break the octet rule for this carbon, and so it has to kick out something. It's going to kick out the bromine. And so what we're going to end up with as our product is something that looks like this. Okay, this is going to be that is horribly drawn. Let me draw that out better. We're going to end up with a product that looks like this. Okay, because this carbon-carbon bond got a new pi bond there. So this is the result of our E2 reaction. Let's compare it to our desired product. Well, we're actually very close. So unlike last time, we did get a double bond, but now the double bond is in the wrong place. Okay, this double bond is on a less substituted position here than it is here. So what we actually got here is something called the Hoffman product. It's the less substituted alkene that forms, but we want the Zaitsev product, the more substituted alkene. Sorry. So let's try option C. So we saw that options A and B were both wrong. Option C is going to have our first step being HBr and ROOR, a peroxide, remember? And our second step is going to be TBUOK. We saw step 1 in option A, step 2 in option B. So if you remember the original 4 options that we had, they were all just variants of one another. So you start to see a pattern. Let's do step 1 first. Well, I'm not going to waste time showing you how to do it again. That's at the beginning of this video. We already did this step. So just remember, for the free radical addition of a halogen, we're going to get the halogen on the less substituted carbon on the alkene. We're going to get, in other words, we're going to get the anti-Markovnikov product. So this is step 1 done. We saw this at the beginning of the video. And now we're going to attack hydrogen with TBUOK. We saw this in step B, so I'm not going to go too in depth here. Well, actually, there's only one possible carbon that it can attack. If this is our alpha carbon, we want to attack a hydrogen on a beta carbon. Well, this carbon is only bonded to one other carbon, and that's this one. This is the only other carbon that it's bound to. And there's only one hydrogen that's bound to. So this is pretty simple. However, if you really stop to think about this for a moment, let me clear this out to make it more clear. This carbon is a tertiary carbon. It's bonded. I keep saying bounded. Bonded to 3 other carbons. So there's a lot of steric hindrance around this carbon, and therefore a lot of carbon orbitals blocking that hydrogen. And so this TBOK, remember, this is your very, very bulky base. It's going to look, this is your bulky base. It's going to have a really hard time attacking that hydrogen. It might not even be able to do it. It actually won't be able to do it. So we're actually going to stop here. This can't perform an E2 reaction. This is completely the wrong kind of reactant that you want. So this is just flat out not going to happen. So that leaves us with one option, and well, just because none of the other options worked, it has to be this one. It has to be choice D. And if you remember what that is our step 1 is going to be HBr, and our step 2 is going to be sodium ethoxide. Okay, so obviously we know that it has to be this one because none of the other ones worked, but let's just see why this one worked. So again, we already did HBr before, so I'm not really going to explain again how that works. Okay, we're going to get the Br on the more substituted side of the alkene. That's why we get the Markovnikov product. And now we have our ethoxide. Again, I don't like to write the Na. You could. In fact, you might actually get more points if you put NaOET. But I like to have OET because the Na is actually not going to do anything. It's a spectator ion. Well, this OET is a lot smaller than the TBUOK, so it's going to be able to attack more different kinds of hydrogens. So let's label our alpha carbon, and let's label our beta carbons, and let's draw the hydrogens around them like we did in you know what, I don't remember which of the options we did it. I did so many takes of this problem that I don't remember which one it is, but you get the picture, right? We're drawing the hydrogens around it. We did this earlier in the video, and we want to figure out which hydrogen is this OET going to attack. Because it can attack any of them, theoretically, right? Because it's small enough to attack all of them. It's not going to be bothered too much by steric hindrance. Well, now the question becomes, where will the most substituted alkene form? Because the alkene is going to be more stable the more substituted it is. So let's say, I'm going to erase the hydrogens really quickly. Hopefully you remember where they are. And I'm going to do the alkenes, potential alkenes in this orange color, a yellow color. So let's say we put it here, right? Well, remember that this bromine is going to be gone. So we're going to have a 1,2 di-substituted alkene. So this would get us a di-substituted alkene. Same over here. Again, di-substituted. But if we put it over here on this bond, well, we'll have 1, 2, 3, 4 different groups that it's bonded to. This is going to be tetra-substituted. This is going to be ultra-stable. And so we want to get our alkene there if possible. Now the question is there any possible hydrogen that we can attack on a beta carbon that would get us to that alkene? And the answer is yes. If we attack this hydrogen up here, then remember this was the hydrogen that was protected almost by this tertiary carbon. So if we attack this hydrogen and we break this bond, we're going to be able to get a double bond here, and we're going to be able to kick out the bromine. And so our end product is going to look like this. This is horribly drawn. Like this. This is going to be our end product, and let's compare it to our desired product. I zoomed out way too far, and look, they are the same. Which means that the correct set of reagents needed to perform this reaction is going to be option D, HBr, and sodium ethoxide.